There we go.
You get it? Yeah. Pretty cool. You kids are here on the ground floor. All over the place. Ready? 5, 4, 3. And welcome back to Mr. Wade's calculus class, pre-calculus class. I mean, we're doing calculus. Don't tell the other schools. Now, today we have lesson 11-2. Who's ready for lesson 11-2? Anybody?
Yeah.
All right. I see you. Okay. Now, let's take a look at this. We have some very interesting cases today, my friends. The first case is a minus plus, and we've got a 0 right down the middle. The next case is also a minus plus and a 0. Odd?
You would think they were the same.
You would think so, wouldn't you? Two identical second derivative tests, yet the graphs, if you already tried to graph some of these maybe, look completely different, not even close. So we have to figure out what to look out for. Okay? We got some morals of the story to talk about today that will help you remember these things. Okay, now let's start off with the first one, which is a what degree what? Third degree binomial, very nice. Kirsten or Stephanie Roberts, very nice. All right. So that's a third degree binomial, and when you graph it, if it's an odd degree, it's going to have to make a snake. Now, it might surprise you though. What I did before I graphed it, I did a little first derivative test for myself, first of all. And I noticed that on the first derivative test, it was not always increasing like a snake does. It was actually an up, down, up. And I think so. Wouldn't it go through the origin? If you plug in 0, wouldn't you obviously get 0? And it turned out that there was a peak on the first derivative test and a valley on the first derivative test. Like that. And remember with the cube, if you put in a square, it makes a bend in the snake, right? And not always, but sometimes if this number is big enough and you put an x to the first, it could bend it as well. Okay? Not always. The x squared is a guarantee. Now, you don't have to know that fact, that's just for fun, all right? The one fact I would remember is that the squared always bends the snake. If you remember that, you're good. Okay? But kind of weird that an x to the first could actually have enough power to bend the snake. So, we have this, all right? Let's label the concavity here. Can anybody see what the concavity is right through here? That's all concave down, hence the double derivative is negative. This is all what? Concave up. So label that on your diagram, F double prime positive. That makes sense. But we've discussed this before. Nothing in math can go from negative to positive instantaneously. Right? Got to be some kind of neutral in between. So point to that little inflection point right there, the origin. And let's label that as F double prime would be what? The concavity is 0. In between the worlds of minus and plus. We did that on Friday. Okay? All right, so that's that. Now, does it match the picture up here? It does, doesn't it? Minus, then we get the neutral marked here, and then plus. There it is. Then we go over here. This is kind of the focus of the day. Something completely different. 1 over x. Do you remember what 1 over x makes? That is a classic hyperbola, right? Okay, very good. Because, first of all, why can't I seem to get to the y-axis? Try plugging in 0 for, what is that 0 in there? 0 for x, right? Okay. Put it. Oh, you can't do it. You can't get there, can you? But you can put in like 1 billion in for x. You can get really close, right? Why can't we get to this one? Okay, it's kind of the reverse of putting in 1 billion. Try putting in a billion. If you put in a giant, put in a Google, right? Okay, put in a Googleplex, your brain will explode, all right? Massive number. If you put in a Googleplex, but you do 1 over that, it's almost 0, but it never gets there, does it? Okay, coming in for landing, so it's one of these. And since it is x to the first, which is odd, it is together or diagonal. It is diagonal. Okay? We did that on a previous test. As a matter of fact, test 7. Okay? So, there's your picture right there. Now, what concavity do we have down here? Concave down. Therefore, the double derivative is negative. What kind of concavity do we have up here? Positive, it's concave up, so F double prime is positive. What about at the asymptote?
No concavity.
Yeah, if the function doesn't even exist, how can you describe the concavity? Can't. F double prime D. Okay? And that is the point of the day. Don't just check the neutrals, check the D and E's, because it does not exist can separate the worlds of concave up, concave down. Isn't that just like the first root test, right? Check your neutrals, but always check the D and E if you can too. Okay? And by the way, this is one of our 3 types of discontinuity. There are only 3 types of discontinuity. You've got a vertical asymptote, or there's a hole in the graph, or we have to have 2 functions to do this one. Disjoint when the piecewise doesn't match up. Right? Very nice. Okay? And this is just one function, so it can't be disjoint here. Okay? There you go. So, remember it's a domino effect. If the original function doesn't exist, then its derivative doesn't exist. We can't talk about slope. And the double derivative doesn't exist, and the third and the fourth and the fifth and all the other derivatives don't exist once the original function doesn't exist. Okay? Domino effect. All right, notice this. Minus, and then we marked the D and E place, and then plus, it's identical except for one thing. And I would probably advise you to label this. We got this from the neutral case, but you got this one from the D and E case. That's really the only difference right there. Okay? So if you label that, you'll kind of know, oh, maybe I should be dodging around this, and then maybe this one's okay, and we'll do all kinds of stuff with that. Okay? All right? Okay, so let's see if we can sum all this up. There are only 3 major things I want you to know about the second derivative test. I'm going to give you the moral of the story, another moral of the story, and on the back page it doesn't say moral, but we'll write it out. But there are 3 morals today. So, first moral, when F double prime is positive, F must be what? Concave up. When F double prime is negative, F must be concave down. And now the most important part of this moral of the story. Therefore, F can only change concavity when F double prime is either 0 or does not exist. That's when the change happens right there. Okay? If you're neutral, maybe you're going through a change. But if your does not exist, you could have a change in concavity. Okay? All right, there you go.
Not necessarily with the B&H, right?
Not necessarily, but there's potential to be there, right?
And with the 0, it's for sure.
For sure, yeah. Very good. Okay. All right. Now, let's see. Case B. In case B, once again, oh my gosh, Mr. Wade, what have you done? We have 2 functions who produce the same double derivative test, but they're completely different. Huh. How about that? Okay.
Candy corn.
Or it's a B or candy corn. Okay, all right. So, I can save a lot of marking. Okay, so here's what we have. On which interval or intervals is this concave up? And you have the same exact test. Okay, first of all, let's draw it. All right. Who knows something about x to the 4th? That is parabola a little bit steeper than x squared. Okay, like that. And over here, who knows something about 1 over x squared? Another hyperbola, but it's an even power. They must be together. Matter of fact, are they together above or below the x-axis? Above, because 1 divided by any number squared would be positive, so it's above. That always is. Except, of course, at 0, it doesn't even exist. Okay? There you go. That was also the test center. All right, so we got our pictures, and you know what? It actually does, in a very strange way, match the same derivative test. Huh. Yes. All right. I'm going to stop it and.
No, because we only have
Or,
left and we started.
Oh, okay. Hey, we're back from commercial. Okay, so here we go. Let's see. This is concave up. If this is concave up, then the double derivative is positive, right? Label that. If it's concave up over here, the double derivative is positive. Now here's a little trick right here. Is it concave up all the way through?
Yes.
Okay. It is, but look at this. Who knows the double derivative of x to the 4th off the top of your head?
4.
Okay, take 2.
No. 12x to the square.
Yeah, good, 12x squared. Everybody see that?
12x squared.
Okay,
12x to the square.
close enough. All right, two derivatives of this would be 12x squared. If you plug 0 in for x into 12x squared, what do you get? You get 0. Interesting. So the double derivative is 12x squared, you put in 0, and the double derivative is 0.
Nope.
But it's a false reading. Don't we know that it's actually concave up right there? Okay? And if you notice, it's plus plus on either side, so it's a false reading, okay? Look at this, I got a big fish on my fish finder. No, it's just a tire, all right? Okay? So, F double prime can be neutral, but it still be concave up. That can happen by accident sometimes, okay? So don't worry about that. All right, so that's that. Now over here, F double prime is what? Positive. F double prime is still positive. But if the function's not defined, you can't define the concavity. So F double prime does not exist. Okay? Fits the same up here, identical, except for one little thing. We probably should note that the 0 came from the double derivative equal to 0, whereas this 0 came from the double derivative, meaning does not exist. Okay? There's a difference, of course. So it's good to label that, otherwise you do have the same test, and you want to label these, all right? Now, let me tell you why you want to label these here. Because we have to figure out the answer to this question, which is, where are these functions concave up? Okay? On what interval? Well, let's see about that. Okay? To dodge or not to dodge? That is the question. Okay? It's a new game called to dodge or not to dodge. All right? Should we make this negative infinity to infinity, or should we dodge around the 0? Wasn't this function always concave up? Yeah, always. So it's concave up from negative infinity to infinity. Okay. What about over here? Oh, dodge the 0, right? It was not concave up at the asymptote, but everywhere else it was. So when we say negative infinity to 0, union 0 to infinity. Now here is the catch. If you look at the graph, isn't it pretty obvious where it's concave up to answer these questions? But you won't always know what the graph looks like. You won't always have the benefit of the graph. Some of these are weird, you don't even want to graph them. So remember the moral of the story that if you can't see the graph. If it's a 0, you just go right through it. But if it's a D and E, you dodge around it. Okay? So that's why I note these on my derivative test, right? So there is no disruption in concavity, or for the first derivative for that matter, slope, if the double derivative is blank. 0. Okay? But there is a disruption in your concavity if the double derivative is D and E. And if you remember that, you'll know which case to use. Okay? And now for this commercial break.
I just want to see my card.
Oh yeah, I'll probably do it during lunch, I think. And plug it in. I just can't do it now because we're on camera on YouTube.
You're on my schedule.
No.
You.
Steve, Chiavo, don't say that.
Pissed.
Okay? You heard him right there. Okay, now, all right, let's flip this over. And let's look for the keyword. And the one keyword here is what? Inflection. Okay? As soon as you see the word inflection, let's go straight to the double derivative. All right. So that would be, let's see, let me write this out first. 27 over 4, x squared, minus 2. Ooh, I don't want to do the quotient rule on that. I mean, I guess you could do the quotient rule, but...
Bring it up.
Yes, it is. You're going to get a heart attack one day. So,